All right, so let's go over energy sources. So in this presentation, I'm going to go over some differences between renewable and non-renewable energy sources, go over some of the fossil fuels, look at the difference between fossil fuel and nuclear, look at some different types of renewable energy, and then sort of investigate carbon-free energy sources. Okay, so first, non-renewable fuels or non-renewable energy sources, often just called non-renewable. So what are they? There's a couple of ways that people define them, but the most sort of accepted definition is that it's an energy source that's not renewable on a human timescale. And so this may seem like kind of a weird way to think about it, but if you think of a human timescale, just think of maybe a few decades basically, so 30, 40 years. So if something can renew itself on the order of a few decades, then it's considered renewable. So most renewable sources, we'll go over this in a minute, but most renewable sources like sunlight, they come back right away, and they kind of renew themselves immediately. But if you think of things like trees and other biomass materials, they take a little while to grow, but they will grow back over a period of time. So that's a human time scale is 10, 20, 30 years, give or take. But non-renewables are not renewable over a human time scale, so they take a lot longer to renew. So the main non-renewable resources that we use are called fossil fuels, something you've probably heard of before. So what do you think, how do you think fossil fuels are defined? So feel free to press pause. So fossil fuels are defined as fossilized hydrocarbons derived through natural processes from organic material. We're going to unpack that definition in a minute, but first what are the three main fossil fuels that we use in the world? So we have coal, oil, and natural gas, okay? I'm sure you've heard of all of them. So those are the main fossil fuels that we use. Now the question is, what does this definition really mean? So what's a fossilized hydrocarbon? So what's fossilized? If you think about what fossilized means, think about that. Think about what hydrocarbon means and think about what organic material means, because this actually is a very important description because it gives you an idea of where these sources come from and what they're made of. So if you think about it, fossilized means it's basically converted from its original form. It's ancient, it's old, it's converted after being buried under rock for a long period of time, for millions of years. So fossilized just basically means old, like a fossil. Hydrocarbon actually means that it's made mostly of hydrogen and carbon. Okay, so if you look at the the chemistry of these, you look at the chemical components of all of these fossil fuels, they would be mostly carbon and hydrogen molecules, hydrogen and carbon atoms, excuse me. And then the organic part means they came from living or recently living material. Okay, so they were recently living, which may seem crazy because, coal is a rock. It's obviously not alive now, but it did come from living material. And so that leads us to our next question. Is how are they formed? Okay, so think about how they're formed, see if you have any idea. That was in the reading and videos. Okay, so first of all, let's look at petroleum and natural gas, so oil and natural gas. The reason they are lumped together is because they are always formed together. So when you find a natural gas deposit, you're going to find an oil deposit. If you find an oil deposit, you're going to find a gas deposit. And so remember, this is fossilized organic material. So these were once living. So the energy in the oil and natural gas came from living creatures. Now this, even though this is from a good source, this is from the Energy Information Administration, it's not like oil and natural gas are made of, giant worms and squid and, manta rays and so forth. More often than not, the original components of oil and natural gas were these microscopic organisms that were floating on the top layer of shallow seas. So if you think of phytoplankton, I don't know if you're familiar with them or not, but they're microscopic and they're photosynthetic, so they generate, they absorb sunlight, generate biomass and energy, just like a plant does. And so the original, these start out as there's just layers and layers and layers of these living creatures, okay? And what happens is, well, let's look here, they die and they sink to the bottom, and they kind of start to accumulate. Then more grow on top, they die and sink to the bottom, die and sink to the bottom. So over time, you have this big, thick layer of biomass. So at the bottom, and this is happening right now, by the way, if you go to the bottom of certain parts of the ocean, there's going to be thick mats of this organic material. And so you have this thick mat of organic material, and then if there's a mountain nearby and it erodes and washes over, and basically just ends up burying this organic material. So these you have this sand and silt and other materials that bury this big, thick organic layer, okay? And then over millions of years, it ends up as an oil and gas deposit. And that's really how it works. So interestingly enough, oil and natural gas they used to be living creatures that just sunk down on the bottom of the sea, got buried, took a few million years, all of a sudden you have oil and natural gas. And so what you end up with, usually when you have oil and gas, you're going to have, if you look at rock layers underground, they're usually curved and bent and so forth because of, uplift and other geological processes. But so you normally, when you want to drill for oil or natural gas, you just shove your well down through here. And what happens is, actually, we'll get to that in a minute. So you're going to drill down through here, capture the oil, and try to pull it up. So the question is, so where is the oil and gas? Like, is there a big pool? So this down here, is that like an open pool of oil? Is it like slushing around underneath the ground? I don't know if you've ever thought about that. But actually, it turns out that's not the case. So oil and natural gas, believe it or not, if you encountered it under the ground, it would look a lot like this. So it actually exists inside the pores of rock. So if you would take a microscope and look at, zoom into this rock, this is sandstone. So sandstone is the most common rock in which you find oil, okay, and natural gas. And so if you would zoom in, you would actually see, even though it's a solid rock, you would see that there's actually these pore spaces in between the sand grains, okay? And if you notice, there's actually little pathways between each pores. So this has, there's space inside the rock for the oil to fit. And if you go back to how it was formed, as this turns into oil, it's kind of seeping up into these sand formation, and then the sand and silt is a siltstone, which is like a sandstone. And as it sort of seeps up inside of these grains, and then this forms into a rock, ends up like this, the oil, natural gas stays in there. Okay, so what's really interesting is that the oil, natural gas, so if it's buried under a lot of rock, I mean, this can be miles down underneath the ground, there's a lot of pressure down low, and it's lower pressure up here. And so if you know anything about pressure, I mean, if you have really high pressure down here, it naturally, anything that's a liquid or a fluid, excuse me, it sort of tries to get up to the lower pressure areas. So the oil, natural gas actually slowly seeps up through these rocks. So all these little pore spaces in here, it actually seeps up through there. And then when you get these oil and gas deposits, when the oil and natural gas hits this layer, so if it hits a layer that it can't go through anymore, it sort of stops and more seeps up through those pores, and it ends up being deposited right there. So if you can find those spots, that's where you would drill your well. And so that's really what petroleum geologists are looking for. They're looking for certain formations of rock that they know that this oil and natural gas is known to exist, and then hopefully they hit a cap rock, and there you have it. Okay, so that's where that is. Okay, so what about so that's oil and natural gas. So what about coal? Coal is formed through a similar process, except that there's two really important differences. One, it's all plant material. Okay, so there might be a little bit of animal material, but it's almost entirely plant material. And two, instead of forming in a shallow sea, it actually forms in swamps. So if you've ever been to a swampy area, I don't know if you've ever been to one, and if you stepped into it, you'll notice that the bottom is very like mucky and sticky. And so that's all this dead organic material. So in a swamp, it's usually very humid, it's usually in a warmer location, And so you have this constant growth or consistent growth of organic material that'll die and sink to the bottom, and then more grows and dies and sinks to the bottom, and so forth. You end up with this big, thick layer of organic material, just like oil and natural gas, big, thick layer, and then if that gets buried under rock, throw it in there for a million years, bada bing, you have some coal deposits. And so coal actually goes through a couple of phases. I'm not going to get into the details, but it starts out as this sort of brown, sort of softer coal, and then it ends up the stuff that you see, the black coal, like you would see here. So this is anthracite. So that's sort of the densest coal um, that is out there. So there's some lighter versions of coal that's a little bit brown and softer. Okay. So anyway, that's how coal is formed. Very similar to oil and natural gas, but it's all plants and it's formed in a swamp. Okay. All right, so that's our fossil fuels. So remember, we're still in the non-renewable category here. So what about nuclear? So nuclear is non-renewable. The question is, where does nuclear come from? Is it a similar process? Well, as it turns out, nuclear actually comes from supernova, so basically stars, so it's extraterrestrial. So any the element we use mostly for nuclear is uranium. Okay, so U-235 is the isotope we normally use. And so nuclear, if you recall from an earlier lesson, is extracting, it's the energy that exists in the nuclei of the atom. Nuclei is the base, of the word nuclear. And it is not nuclear. I do hear that from time to time. It is not nuclear, it is nuclear. If you look at it, nuclear, okay? Anyway, so all the uranium came from outer space, actually. So when the Earth was formed billions of years ago, we had this uranium naturally in there. So the bottom line here is that we're not getting any more. Whatever uranium is in the Earth's crust is there, and we're not getting any more. Okay, just like oil, natural gas, and coal, whatever's down there, for all intents and purposes, I mean, yes, it's still forming, but it takes millions of years to form. So for our purposes, it's not renewable because it's going to take another, 50, 100 million years for more to form. Okay, so pretty much all that's there is there. With nuclear, it is not even forming right now. So whatever's there is there, and that's it. So the question is, how do they get nuclear material? So most uranium is mined in rocks like this, or there's these underground deposits that are kind of intermixed in the soil, and you can bring it up and then refine it through various means, and you end up with this powder. So anyway, it's a little different than oil and natural gas and even coal, and you end up with this sort of powder, and then you refine that and put it into pellets, and that's what you use. Okay, so the bottom line here is that all the non-renewables, we have the fossil fuels, and then we have nuclear. Nuclear is non-renewable, but is not a fossil fuel because it's not a hydrocarbon. It's not derived from organic material. Okay. All right. So there's also a difference between how we extract the energy out of coal, oil, natural gas, and nuclear. So how do we actually get the energy out of coal, oil, and natural gas? So you press pause and think about it. Really, we burn it, right? So you burn it, and that's how the energy is released when you burn it. We'll go over that in more detail later. But what about nuclear? Do we burn it? Do we set it on fire? And the answer is no, we do not set it on fire. Okay, so let's look at the difference here. So first of all, coal, oil, natural gas, we burn it, which is just combustion. So combustion, without getting into too much detail, you don't need to know all these details yet. We'll do this later. So combustion, if you have a fuel source, in this case, coal, oil, and natural gas is our fuel source, you add enough oxygen and heat. So any of you that have started a fire before knows that you need oxygen to feed the flame, and you need heat to get the flame started, then you need heat for the fire to continue. Okay, so these are the sort of the three legs of the stool of combustion. You need these three things. If you take any one of them away, combustion will cease. So for our fossil fuels, you have combustion, and there'll be some impurities, like there'll be some sulfur in the coal or some nitrogen oxide or whatever. Okay, so there will be some impurities, but the main part of the combustion is here. And so the three legs of the stool. And so after combustion, the byproducts you get are carbon dioxide. So remember, these are hydrocarbons, right? So mostly hydrogen and carbon. So this fuel source is hydrogen and carbon. You add more oxygen, you end up with carbon dioxide, water vapor, and then you end up with more heat. I mean, that's, if you burn a fire, you're releasing heat. And so what's really cool about this process is that the heat then actually goes back to feed the heat. So this heat that comes from the as a byproduct actually goes back and feeds the combustion reaction, and then it can continue on and on and on until as long as you have these three sources. Now, of course, carbon dioxide is a really important one that we're going to consider in terms of climate change. And so remember that carbon dioxide results as a result of combustion of fossil fuels. Okay, so what about nuclear? So nuclear actually we don't burn, so we get it through fission. So fission is just the splitting of these atoms. Okay, and so the basic process here is you fire this neutron. This is a simplification of it, but basically you fire a neutron, you hit the uranium, okay? So then it becomes unstable, it splits apart, and so when it splits, the really interesting thing about this is, first of all, this split is called fission. So what happens with this split is it actually releases more neutrons, but it also releases energy. Okay, so it releases energy, but it releases more neutrons. So if you can imagine then, if you release these extra neutrons from this original atom, so you're splitting it, releasing energy, releasing these neutrons, well, guess what? Those neutrons hit other uranium atoms, right? And then splits those, and then they split and release their energy and release more neutrons. And so you can see the more this reaction continues, the more it just continues to split more and more uranium, which then releases more neutrons, which splits more uranium, and so forth. So it just keeps going on and on and on. And all the while it's releasing heat, which is why nuclear is so powerful and dangerous at the same time. I mean, it's very powerful because you know, if you look at the size of these uranium pellets, they're not very big. They can generate a lot of energy. Okay, but the problem is, and this is what nuclear bombs take advantage of, is that this is an out of control chain reaction that just releases a whole bunch of energy. Okay, and so it's different than combustion. We're not burning it, we're actually splitting the atoms. Okay, so that's it for the non-renewables, and in the next video I will go over renewables.